So up we have the next presentation. It's my pleasure to introduce Jorge Gomez from Reality Labs at Meta. And he's going to talk about distributed on-sensor compute for AR and VR devices. And it's a semi-analytical simulation framework for power estimation. So with that, I'll let him take it from here.
Thank you. Well, thank you for the introduction. Today I will talk about our work on distributed on-sensor compute system for AR, VR devices with a focus on a semi-analytical simulation framework for power estimations. So the first wave of personal compute was characterized by the device that we see today in the world, such as personal computers, tablets, and cell phones. Augmented reality and virtual reality glasses, we believe, will be the next big wave of human-oriented compute. Those devices can mix virtual content with real world freely. So augmented reality glasses can do the same that cell phones can do today with much less friction. Augmented reality glasses can augment with virtual content via a see-through display our reality, such as the virtual chess that you can see over there. And of course, this will enable us to share content, such as virtual objects, avatars, or a control panel for shared workplace, etc. So these augmented reality glasses can sense your world from your own point of view. So that enables to enhance our cognition, perception, and memory. For example, here, they can provide key statistics during a business meeting, or they can also do translation on the flight. So we know that augmented reality glasses are extremely complex systems with multiple heterogeneous components with stringent requirements in power, weight, and performance. Also, the glasses must have a socially acceptable form factor. So some of the components that this device has are, for example, sensors and cameras to pinpoint our location and also enable hand tracking and eye tracking, displays and optics to overlay high-resolution, sharp virtual content on our view of the reality, CPUs, GPUs, and AI accelerators to, of course, do all the compute, memories, microphone, and speaker. So this complex system also gives us a huge amount of opportunities to optimize it. So we need a comprehensive system simulator to explore all this complex design space. So the outline of this talk is the following. First, I will talk about the difference between centralized and distributed compute system. Then I will very briefly introduce our smart image sensor. Then I will talk about the simulator that we are presenting in this talk. And finally, I will show an example and the result of that example. And finally, we will conclude. So let's get started with the centralized and distributed compute system. So here, I'm showing a multi-camera system in which we have, of course, the image sensor that sends the raw sensor image data through the serial interface to typical MEP to the processing unit, in this case, the aggregator. On the other hand, in a distributed sensor compute, we will have a smart image sensor, in which the camera is very close to the on-sensor processor. And we can connect the camera to the on-sensor processor through micro TSV that has a low energy and high bandwidth. Then we only send high-level data representations to the aggregator through MIPI. So this localized compute enables us to have huge benefits in power, latency, and privacy. Also, here a key component is the optimal repartition of the workload between what we are going to compute in the on-sensor processor and what we are going to compute on the aggregator. So let me quickly introduce our smart image sensor. Well, this smart image sensor is enabled by triple wafer stacking technology, in which the first 2 layers are our image sensor that is connected to the logic layer through through silicon via. In the logic level, we will have an ML accelerator, of course, SRAM, and also weight storage. We know that current DNN requires huge amount of weight storage. So if we implement that with SRAM, it will be very costly in power due to the high leakage of the SRAM and in area. So in this work, we propose to use MRAM that has low leakage and high density. We also know that, of course, MRAM has a high write energy, but because we're using it as weight storage, we will mostly read it. And the read energy of MRAM is comparable to the read energy of SRAM. So now let me quickly introduce how we are planning to do the workload partition between the on-sensor processor and the aggregator. So here I'm showing a cartoon of the system in which we have the smart image sensor and aggregator, and part of the workload will be compute on sensor and part of the workload will be compute on the aggregator. So the key idea here is that the activation size of our neural network will change during the workload, and we want to send this activation size through the energy-hungry MIPI at the point of max compression of the activation size, when the activation size is smaller. So now that we have all these key concepts of the distributed compute system, we can go to our simulator that we're proposing in this work. So first, we start defining the system that we will use, the number of cameras, on-sensor processors, aggregators. Then we define each one of the modules, which type of camera, which type of interface, which type of on-sensor processor. And then we'll define the key technologies and enablers of these modules, like technology node, SRAM or MRAM, etc. Once we have defined our system, we can define our applications. First, we define the workload, such as eye tracking or hand tracking. Then the workload optimizations that we are going to do, such as pruning, quantization, etc. And then the optimal distribution. That refers to how are we going to distribute our workload in this system. Of course, this model can be used in an iterative way. So we define one splitting point, and then run all the model, and then we can come back and define another one, and then compare the power, latency, etc. Then all this information go to the toolchain. And finally, we have the simulator, in which we will have a camera simulator based on analytical expression, an interface simulator, and an architecture simulator. From the toolchain, we get the activation size and the instructions, and from each one of these simulators, we can get the energy, delay, and area. Then we can sum the contribution of each one of these simulators, and we get the total system power, system delay, and system area. So now that we introduce briefly the simulator, let's go to an example. So here we introduce the hand tracking algorithm that is basically composed of 4 cameras that has an image sensor, of course, connect to micro TSV to a non-sensor processor that is running DetNet, that basically extract the region of interest of our image. So these 4 region of interest are sent through MIPI to the aggregator that extract the joint location using KeyNet. So here, main takeaway is that we can run DetNet at a lower frame per second in the on-sensor processor. So how are we going to calculate the total energy? Well, we calculate the total energy per frame adding the contribution of each one of the elements. So we add the contribution, sorry, the pointer is tricky. We add the contribution of each one of the cameras, each one of the interfaces, and of course, of each one of the processors and each one of the memories. For all these analyses, we use technology parameters from leading foundries. Here, in the simulator, as I was saying before, for the camera and the interfaces, we use analytical expression. Also, for the processors and memories, we use existing architecture simulator merged with our own analytical expressions. So here I'm showing you just an example of the architecture simulator. As I was saying before, we use existing architecture simulators such as GVSOC, ScaleSim, or time loop to characterize the processors that we're using. Of course, which simulator we use depends on which architecture we are targeting. For example, here, we use GVSOC to model the architecture that I am showing here, in which we have an L2 memory that has MRAM for weight storage and SRAM for activation memory. Then we have an L1 memory and an accelerator. Then, using GVSOC, we can extract the performance of each one of these layers, depending on the arithmetic intensity, and characterize our own workloads. So here, I am showing the well-known roofline plot, in which we plot the throughput versus the arithmetic intensity, and we characterize each one of the workloads in which, each one of the layers in which we are interested, depth-wise convolution, point-wise convolution, or regular convolutions. So now let's go to see the complete simulation results. So here I'm showing the camera system normalized power consumption. In the y-axis is the normalized power, normalized to the centralized system, and in the x-axis is each one of the scenarios that we wanted to explore. In blue, we show the power consumed by the camera. In green, the power consumed by communication, orange by processing, and pink by memory. So the first takeaway here is that when we go from a centralized system to a distributed system, we see a power reduction of around 24%. This power reduction comes mostly from a reduction in the communication power, because we're sending less data through the energy-hungry MIPI, and also we get a big improvement in the camera power, because due to the high bandwidth of the micro-through-silicon via, we can reduce the readout time of the camera, so the camera can stay a longer time in a low power mode. Then, if we change the technology of the on-sensor processor from 7 nanometer to 16 nanometer, of course, the power increases, but is still lower than the centralized system. Now, if we replace the weight storage for MRAM in the distributed system with on-sensor processor in 16 nanometer, the power, of course, goes down again with an improvement also in area. So here I am focusing only on the on-sensor power, in which, again, in the y-axis, I am plotting the normalized power, and in the x-axis, we are plotting two scenarios, when the weight storage is SRAM and when the weight storage is MRAM. And we see an improvement of around 39% in power that comes mostly from a reduction in leakage thanks to the MRAM. We also have an improvement in area that comes from the high density of MRAM. So now, finally, the conclusions. So as you saw, we developed a semi-analytical simulation framework for AR/VR distributed on-sensor compute architecture to study how the different technology parameters impact our system. In the case of hand tracking algorithm, the model predicts that going to a distributed on-sensor processor system, we see a reduction on power that comes mostly from improved communication power, because, again, we're sending only a small activation size through the energy-hungry MIPI, reducing the camera readout time thanks to the high bandwidth of the micro-through-silicon via, and a reduction in leakage thanks to MRAM. Also, NRAM allows us to reduce the area of our sensor. Thank you very much, and I will be happy to answer any questions. Do you refer to, the algorithm or to the algorithm or the architecture?
The algorithm uses to optimize.
Yeah, that is a very good question. We do mostly an heuristic search. So basically, we test every possible scenario. So we run this model in an iterative way and then compare the results of power latency for each one of the cases.
So like a grid search of some kind?
Yeah.
Okay, and isn't the design space too large for a grid search, or did you just run it for a long time, the search?
Sorry, can you repeat?
Sorry, is the design space too large for a grid search?
For the workloads that we are showing here, no. But most of this model, we have a lot of analytical expression on it on purpose to have like a high speed of running. So we can explore. This is like a first level exploration of the design space. So we can explore very fast all the different combinations. I don't know.
That sounds good. Thank you.
Hey, thanks. Yeah, interesting work. Couple of clarification questions. So in your model, you sort of don't assume any collisions and stuff. So I'm assuming that your system is designed so there are no conflicts, or if the sort of any traffic collision that's happening because of multiple data movements and stuff, where is that taken care of? Because it seems like you are aggregating everything, so your system is sort of over-designed or just enough designed so everything is deterministic?
Yeah, for now, that is a very good question. As I was saying before, this is a first level of exploration. Mm-hmm. So most of the data transfer are solved now with analytical expression. So we are not dealing now with some, I don't know, stalling or, of course, on the processor, yes, but on the data transfer, no. But yeah, if you want, we can go to, because the paper explains in detail how we solve each one of the problem. So we can go through that later, because I don't know to which one you're referring, because there is like a lot of specific elements in the system that claim can apply to. So if you want, we can go through that in detail later. I don't know.
Okay, and just along these lines, another clarification question is, so sort of you show that your MRAM power savings is coming, largely because of leakage. So I'm assuming the sort of the application here warrants that most of the components, they're not sort of, gated that can, save power through SRAMs. I mean, everything is active, or I'm wondering that, there are tricks you can do that you can save power while you're using SRAM. So how much of that is explored and stuff?
Yeah, that is a very good question. Of course, we optimize the application to work well with MRAM. So as I was saying before, a key takeaway of the hand tracking algorithm that we choose to demonstrate that is that the algorithm that we are running in the on-sensor processor can run at a smaller frame per second. So we can use the same region of interest for multiple frames. So that means that the activation time of the on-sensor processor is small, so the leakage has a bigger impact.
I see.
So we optimize basically the application, yeah.
Okay, yeah, thank
for
you.
The technology.
Thanks again for the presentation.
Thank you.
Yeah, I think we probably have time for one, maybe two more questions.
Okay, I'll be quick. Yeah, very nice presentation. One quick question about comparison between SRAM and MRAM. Which technology node did you assume?
16 nanometers for this comparison.
16 nm. And what is the size of the MRAM which you are assuming?
I prefer if we talk later about that, because
Sure.
yeah, I prefer to talk later about that, if that is okay.
Okay, no problem.
Yeah.
Thanks.
Thank you for the presentation. For the hand tracking, you mentioned there's a DetNet and a KeyNet.
Yeah.
It seems KeyNet is the recognition part and DetNet is the detection part.
Right.
So for hand tracking, it seems like you need something online, right? So I'm kind of curious for the distributed computing, like when you get the recognition on the server and then send back to your camera, or your glasses? Like, did you do analysis on the latency round trip?
No, here everything is localized on the glasses. All the processing is done.
Oh, even the
we
distributed
don't
part?
go online for the
Okay.
hand track.
So the distributed computing is also on the glasses?
Yeah,
Okay.
on the
interesting.
aggregator.
Thank you.
Thank you.
Okay. Thanks a lot, everyone, for the questions, and thanks again for
Thank you.
the talk. Yep.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. Gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymix, HOTG, Imagimob, ITMIS, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texil, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.